So far we've been talking about the electronic structure. Now let's just digress a little bit and talk about constraints in classical molecular dynamics, which will help us then understand the Parrinello algorithm. So in classical molecular dynamics, I was talking about nuclei moving and no electronic structure involved. Sometimes we want to fix the value of some structural parameters. So for instance, a bond length, but it could be an angle that's formed by 3 atoms, or it could be a dihedral or a torsion angle that's formed by 4 atoms, or any other constraint you can think of. Why do you want to do that? Well, as we discussed before, then if you're freezing a rapid variation of position of atoms, then you can actually afford a larger time step. So that's one way of accelerating the simulation, because you want to get rid of degrees of freedom that are not interesting, typically OH, CH, or NH vibrations that don't really, that are not really what you want to study. There's another reason, though, which is related to more advanced sampling techniques in molecular dynamic simulations. So this one is called thermodynamic integration, and I will not explain in detail what that is. It's another lecture in itself. But basically, try to think about what would happen if you try to study a reaction barrier. So suppose you have a molecule that reacts with another one, and let's say that you find some convenient reaction coordinate. So for instance, some atom is transferred from the first molecule to the other molecule. And you'd like to understand what the barrier is, the energy barrier is for this reaction. Now, if you just take the 2 molecules and force the atom to go from one molecule to the other, well, you will get something. You will get some energy that increases when the atom is removed and then decreases again when it reaches the other molecule. But that is usually not a very precise description of what happens, because what happens in reality is that the molecules are at finite temperature. So what you're interested in really is what's the energy barrier that you see if you transfer that atom from one molecule to the other as they are vibrating, which is a different problem. So what you really want to calculate with is a free energy barrier. It's not just an energy barrier. So if you can run molecular dynamic simulations, you can actually study that at finite temperature. Suppose you want to compute this free energy barrier. Well, you would run your molecular dynamic simulation with the 2 molecules. Now, if you just run the molecular dynamic simulation of these 2 molecules and you wait for this reaction to happen, it's going to take forever, right? Especially if the barrier is somewhat high. The chances that at some point you will have sufficient kinetic energy of that atom to go over the barrier is very slim. So you can waste your entire computer budget and nothing will happen. So you want to sort of force this reaction to happen. So in that case, you could use constraints to force that atom to go away from the first molecule and reach the other molecule, while everybody else is moving around and vibrating at a given temperature. So that would be an example of thermodynamic integration. If you do that, and it's a little bit more subtle than what I'm saying, there's a cartoon explanation, but if you do that and you compute at each time step the force that is actually acting on that constraint, then if you integrate that force over the whole trajectory, then you can get an idea of the energy barrier. So this is a sort of more advanced MD technique, and it's actually very interesting to use that in the context of ab initio MD. Because remember, when we use classical MD, we have to choose a potential that describes the interaction between atoms. Now, if you have 2 molecules, maybe you have a good potential that describes molecule A or molecule B, but usually these potentials are not that good at describing what's in between when the atom is actually crossing from molecule A to molecule B. That's where having density functional theory is really useful, because we have a realistic description of this process of the transition between the two molecules. So that would be another case where it would be useful to impose a constraint to atomic motions and have this constraint, for instance, the bond length between this atom that has to transition between the 2 molecules and another atom of one of the molecules. And you want this length also to change in time. You want it to slowly go from one to the other. So for instance, in code that we used yesterday in Qbox, you can actually do that. You can specify also the velocity of that constraint that will stretch that bond. All right, so those are sort of justification for using constraints. How do you include constraints in a molecular dynamic simulations? Well, the way this is done is basically this. You first compute the molecular dynamics step, ignoring the constraint. And then you do something to restore the constraint. Okay? So the first part is easy. You just ignore the constraint. So you just do what you would do otherwise. Now, what we're going to discuss now is how do you actually restore the constraint after each time step. Usually those algorithms that restore the constraints are iterative. You have to apply several iterations of a correction to the atomic position to restore the constraint. The one that we're mostly interested in is called the shake algorithm, and that's described in that paper here, right from Gygi. And that's the basis for most of the constrained MD algorithms that we implement today. So let's do a little bit of math to describe constraints here. Suppose you have a vector x. That's basically describing your atomic positions. Okay. So I just call it x in Rm. Now m is going to be 3 times the number of atoms, right? For each atom, you have 3 numbers to describe the position. So m will be 3 times the number of atoms. This is the vector that describes atomic positions. And now suppose that I have defined n constraints, not just one, but the number of constraints on my system. Now mathematically, I can express that in this way. I can say I have n different functions, sigma, that must be equal 0. And I don't specify what these functions are, but the constraint is imposed by making sure that x is such that these functions are 0. Okay? You can see that this equality here for n different functions reduces the number of degrees of freedom that I have by n. Okay. So let's see what this function looks like. A simple case of a distance between 2 atoms. So in that case, my vector x is just the 3 coordinates of atom 1 and the 3 coordinates of atom 2, and that's a 6-dimensional vector. And if I want to define the constraint of distance between the 2 atoms being equal to d, then that's going to be the function sigma. Right? It takes the difference of the coordinates x and squares it. Same for y, same for z. And then minus d squared, which is the distance I would like to enforce. This must be equal to 0. Okay? So if the constraint is satisfied, sigma of x is 0. So what we're going to be doing is we're going to make unconstrained steps, which make sigma become non-zero, and then we will have to restore the constraint to get back to sigma equals 0. Okay?
So these constraints are only of the depend on the position of the body.
That's right.
If there is some kind of angular rotation or something, is there an equivalent constraint to restrict them? For example, there are many molecules where side molecules can go into a vibrational or different kind of modes.
That's possible, and that means just that you have a more complicated function sigma. Right? So you can invent all kinds of functions to describe constraints. The distance is the simplest to think about. The angle, the torsion are simple. Sometimes you want to enforce a constraint that one atom is in the plane defined by 3 other atoms. That's a more complicated constraint. It just means that the function sigma there will be a more complicated function of the coordinates. All right, so remember we do this first MD step, ignoring the constraint. So we're going to do that step, and we're going to generate this xu for unconstrained, okay, at t plus dt. So that new position xu does not satisfy the constraint. And now we do something. We have to find out some algorithm that will get back to a situation where the constraint is satisfied. So the point is here that there are different ways of doing that. It's not unique. Okay? If you think about the molecule that is just 2 atoms, and we made a move, and now the distance between the 2 atoms is not the one we want. If could restore that distance in a number of ways. In particular, anything that rotates the molecule and rescales it will restore the constraint. So it's non-unique. But for instance, you might define the problem to be find the smallest displacement that will restore the constraint. Okay, and that mathematically would lead to a least squares problem. Actually, what we want is something a little more specific. We're interested in the so-called holonomic constraints, and holonomic constraints are defined as constraints in which the force of the constraint does not do any work. And that's useful for molecular dynamics simulations because we don't want the constraint to appear in the energetics of the problem. We don't want any work being performed by the constraint. And if we have holonomic constraints, then all the constants of the motion, such as the energy or the momentum or other things like the angular momentum in some cases, those would be untouched by the constraints. So that's a good property. So what we would like to do is have such holonomic constraints, and that will actually determine a unique way of restoring the constraints. So the way this appears mathematically, if you say you want a holonomic constraint, not just any constraint, it means that the corrections you're going to make to the vector x must be basically spanned by the columns of the matrix A. And this matrix A is given by the partial derivatives of these constraints function, these nonlinear function sigma. Okay. So it takes a little bit of time to absorb that, but if you read the paper by Gygi and Parrinello, then a little bit longer time to read it and get familiar with it. But that basically is the condition you have to satisfy to have these holonomic constraints. So now the correction you're going to have to add to your unconstrained position will have this form here. The new position at time t plus dt will be the unconstrained one plus something that is just multiplying the columns of that matrix taken at the position xt, okay, at the current time step. Notice here there is this 1 over mi here. It just is a rescaling by the mass of the particle. That's necessary to have holonomic constraints. So what you need here, what you don't know in this equation is the lambda j. It's the coefficients multiplying these columns. You know that function, okay? You know how to compute that function. That's the way you define your constraint, so you know how to compute that. You know how to take its derivative. You know how to compute that matrix, so A I j is known. But what's not known is the coefficients lambda j. Turns out you can consider those coefficients to be Lagrange multipliers, which is another way of looking at the problem. You have a constraint equation, and the lambda j's are just the Lagrange multipliers associated with a constraint. So basically, if you find those lambdas, you can get back to the constraint being satisfied here at the next time step. Yeah.
So to figure out these holonomic constraints for a particular problem, does one require any experimental information about that particular system? How to figure out to start with, for example?
There's a big amount of literature on that, and the definition of the constraint itself can be arbitrary. What's defining it to be a holonomic constraint is the way you restore the constraint during the dynamics. Okay, that's the right choice if you don't want to affect the rest of the energetics. But you can define arbitrary constraints. You can do very strange things with constraints. We'll discuss some of that later. Okay, so if you want to now find these values of lambda that will give you the right values to preserve holonomic constraints, then you have to solve these nonlinear equations here. And these equations look like this. The matrix A appears here, and it's transposed. Notice that the matrix A is computed at two different configurations here. One at the previous step, which is the one where the constraints was satisfied, but this one is computed at the unconstrained step. There are some keys there that are actually important to preserve these constants of the motion. The matrix M here is the matrix of the masses of the atoms, so it's just a diagonal matrix. So all in all, it means you have to solve this nonlinear equation. It's a matrix vector nonlinear equation, and you use the Newton iteration, Newton's method to solve that, meaning that you have an iterative method to solve the equation. Right? That's the best known way to solve such a nonlinear equation for a vector, is to just iterate with Newton's method. And what you get in the end is called the shake algorithm. So that's what is described in that paper, and that's what is done in most MD codes, classical MD codes. So this is kind of telling you what's under the hood when you activate these constraints in the code, and this is what it does behind the scenes at each time step. Now, this is not a very expensive problem. The dimension of these matrices here has to do with the number of atoms. So it's nothing like the matrices involved in the electronic structure, which have 10,000 by a million, this kind of thing. Here we're talking about maybe a few hundred. So it's some work, but it's not something that will slow down the calculation very much. For people who are doing molecular dynamics for proteins, this is a bigger problem, because that's really the big problem they have. They have hundreds of thousands of atoms. Then they end up with a large problem. For us in ab initio MD, unfortunately, we can only afford fewer atoms, so this is not so much of a problem. Okay, one thing that good to keep in mind when you start using constraints and playing with these parameters is you can actually start having things that are impossible. I suppose you want to constrain distances between atoms. You have 3 atoms. You define three distances that would define a triangle, but depending on how you choose these values might not be feasible. Okay, so if that happens, then these matrices become singular, and the whole thing never converges. So that's one thing to keep in mind, so you don't assume that constraints always work. You still have to think about what it means in the geometry of your molecule, and make sure that it makes sense, that it's possible to realize a constraint.
In this simple example of 2 atomic molecule, so if I impose the constraint of the distance, basically nothing should happen. There should be no motion at all, right?
I'm sorry.
So if I impose the constraint of the distance in this diatomic molecule, there should be no motion at all, right? So, but
just one molecule, there will be no motion at all. Yeah. Or it could rotate.
Well, okay, so I mean, for example, during unconstrained molecular dynamics step, let's say it moves towards each other,
right?
And then I want to restore this constraint. It would not be holonomic, right? Because there is
depending how you do it, it would not be holonomic. Basically, for the case of the dimer, suppose that the unconstrained step has brought you in a different orientation and shrunk the bond. What you would say is the easiest way to restore the bond length would be just to rescale it in its current orientation. Turns out, if you want it to be holonomic, you have to apply corrections which are parallel to the previous orientation. That's where it's a little bit more subtle than just the simplest correction you can find. So that's why you have a little bit of this complex machinery to enforce that. And basically, it means that you have to go back to the orientation you had before and then correct. And that will preserve the constant of the motions. Okay, so we discussed a little bit the bond length constraint, and if you want to force a certain value of an angle, it's a little bit more complicated equations, but it's still the same principle. You still have this first step of unconstrained step and then correct for it. So what happens in QBox, for instance, that you have this list of constraints that you define in the input. You add a bunch of constraints of all kinds you want. And at each time step, it's going to go through that list iteratively and update all of them until they're satisfied. And depending on how many constraints you put and whether they are actually feasible, it might actually declare that, nah, I can't do it. There's a problem. I cannot satisfy all the constraints at once. So this, apart from being of interest for molecular dynamic simulation, is actually interesting to start the issue of Parrinello molecular dynamics. That's, again, a different chapter. So since it's 10:30, I would suggest that we take the break now, a little bit in advance, and we start discussing about Parrinello after the break. Any questions so far?